So in this video today, we are going to go over conditional probability. So if we look at example 1, it says, look at the scenario below. What do you notice about the numerator and denominator of the probabilities that could help you create a formula? So it says a class of 40 students was asked, do you like school? The results are recorded in a two-way table. So we have our males, we have our females. And we have our yes, we like school, no, we don't like school, right? And then we have our totals. So then it says, if we look to the right here, it says, yeah, what is the probability that a student says yes, they like school, given that they are male? Remember, that slash means that's the part that's given. So notice the formula. It has that the given, it says probability of yes and male on top. So our yeses and males is right there, okay? And then it has male on bottom. Okay, and so that's right there. So notice we have a total on the bottom, and remember, our givens are always going to be totals, okay? And then what part of that category of males is the yes? That's the 15. So it's 15 over 20. Now, remember, if you were going to write this answer, you'd reduce that to what? 3/5, okay? Then on the second one, another example, just to kind of help clarify here, it says, probability of females given that they said no, okay? So once again, we're looking at our females here that said no. That's 3 of them. And how many total females said no? Or how many total people said no? Again, that's what goes on the bottom. So this is an and statement, right? Because it's females that said no. This is our total no's. So once again, you're putting your total in the denominator and your females that said no on the top. So conditional probability, this is the way you guys need to look at it. If you're looking for conditional probability of A given B, then the numerator should always be A and B. So you're looking for that word and, okay? And then the denominator should be something single. So, and it's a total, okay? So actually, let's write out here total as well, because that's what that's going to apply to, okay? So now, once again, this is going to be the overlap of two things, right? And then this is going to be a total for the one thing. So the formula is going to be the probability of A and B over the probability of B, because this statement says the probability of A given B has occurred. Okay? So now, example 2 says male and female students were asked their mode of transportation to school. The two-way table shows the results from the survey. Use the table to answer the following questions. Let's see if we can move this over a little bit. There we go. So it says the probability of male given they do not ride the bus. So what are we looking for? We're looking for the total of people that did not ride the bus. We're going to put that in the denominator. So people that didn't ride the bus. So ride the bus is 52, right? So we need the 17 and this 33. So what we're going to do for our total this time is we're going to do 17 plus 33, okay? Because that's our total of people that did not ride the bus. Now you could do 102 minus the 52. But I kind of like it this way better, and it doesn't matter which way you do it, okay? But then it's asking us how many of those people were males. So what we did initially is we took these two numbers, we added them together for our denominator. Now we're looking for people in those two columns, okay, for our numerator. So that's our 9 and our 9, right? So those are the males. So that's 9 plus 9. So this is going to give us 18 over, what is that, 50? Okay, so then we can reduce that, right, to 9 over 25. That could be the way our answer is represented. Or 9 divided by 25 is equal to 0.36, which is equal to 36%, okay? So example 2 says, what is the probability of choosing a person who walks given that the person is a female? So now our given again, this time we're going to look for our total females, right? So our total females are right here. That's 58, right? So we're going to do our 58 as our denominator, and then we're looking for the people who walked that are in that row, okay? So that's 8, right? So that's 8 over 58. That can be reduced, can it, to 4 over 29? Again, you can put that right in your calculator. It'll reduce it for you. That would be 0.14 or what, 14%, okay? So now we got a U-try here for you guys to do. So this one says, what's the probability that someone did carpool given they were male? Okay, let's see if you guys can figure out this one. Pause the video, do it, come back to me when you're done. So here again, we're going to look for the total of what? Males, right? No, yeah. males. So we're looking for the total males. That would be this 44 number right here, right? And then we're looking for how many of those were carpool people. So it's going to be our 9. So it's going to be our 9 over 44 here. 9 over 44 is equal to what? Can that be reduced, 9 over 44? Nope. Okay, so that's 0.20, which is 20%. Yes? So our answer was A. Okay? All right, so we're going to do another example here. It says find each of the following conditional probabilities when you rolled a 6-sided number cube. So how many outcomes could you potentially have? Isn't that going to be 1 through 6 here, y'all? So that's 6 outcomes, right? So that's how many potential outcomes we could have. So then it says find the probability of a 4 given that you've rolled an even number. So how many of those numbers 1 through 6 are even? That's going to be 3, right? And then how many of the even numbers, 2, 4, 6, are a 4? One of them, right? So that's 1 over 3, which is 0.33, which is also equal to 33%. Okay, let's see if you guys can do the U-try. So this one is the probability that you roll, that you get an odd number, given that you got a 1. Pause. Go ahead, do it. Come back to me. Well, isn't that really just 1 over 1, y'all? Because 1 is an odd number. So that's 100%, isn't it? Because 1 is an odd number. Okay? Don't overthink it. All right, so the next one says you pull 2 cards out of a standard deck of cards without replacement. What is the probability that your second card is a 5, given that the first card was a 3? Okay, so we don't replace them. So here's the key. You all see this phrase right here, without replacement? That is really important to what we're doing today. Okay, but the standard deck of cards has many cards, 52 cards. Hopefully y'all know that. If not, this is something you better memorize. And then we have 4 suits in a card. So you have hearts and spades and clubs and diamonds, right? And so each one of them has one of every number. So you have 1 ace in every one of them, a 2, a 3, a 4, 5, 6, 7, 8, 9, 10, right? And then you have a jack, a king, a queen, and a king, okay? So it says, what is the probability that you're, so first it says you pull 2 cards out of a standard deck cards without replacement. So what is the probability that your second card is a 5, given that the first card was a 3, okay? So how many 3s are there in the deck? That's what we're going to talk about first. So we have 4 3s in a deck of 52. Now it says that we take the card out, but we don't put it back, right? So let's talk about how many cards we have the second time we pull. So now when we multiply, we're going to multiply here, okay? So this bottom's going to be a 51. Okay, but it says the second card's a 5. Now, how many 5s are left in the deck? There are still 4 5s, right? So that's going to be 4 times 4 across the top. You're going to multiply across the top, 4 times 4, and you're going to multiply across the bottom, 52 times 51. Okay, so when I do that, I got, what did I get? Pause. 16 over 2652, and then we're going to divide the 16 by the 2652 and then reduce that. So that's going to end up being 4 over 663. Okay? When we find that percent, we would get 0.006, which if we rounded that to a whole percent, it would be 1%, but it could also be written as 0.6%, okay? So 0.6%, depending on what the answers look like, okay? So go ahead and do this U-try here with these 3. So you're red, given that it was a heart, heart, given that it was red, even, given that it was black. So think of how many hearts you have. That's your denominator. And at this time, you're only pulling 1 card, okay? And then you got red, given that it was hearts, and black, given that it was even. So come back to me when you're done. So right, on this next one, it says, so if I look at the number of hearts that are in a deck, that is 13, right? So 13 hearts in a deck, and how many of those are red? All of them, right? So that's 13 out of 13, so that would be 100%. So once again, don't overthink this, okay? So now what's the probability that, given that you have a red card, so this time again, how many red cards do you have? 26 of them. Now how many of those were hearts? That would be half of them, right? Because half of them are diamonds. So this would be 13 over 26, so that's going to be 0.5, which is equal to 50%, okay? Now our last one is, given that it's black, so how many black cards are in the deck again? 26 of them, and how many of those were even? Okay, so this one now we're going to have to think about 2, 4, 6, 8, 10. So for every suit, there's 5 of them, right? So 5 times 4 is 20, yes? So you're going to have to think this through, guys. So 20 over 26, that reduces to be 5 over 13. 5 divided by 13 is 38.038, okay? So that means it is 38%, okay? All right, so on this last part of the lesson, it says probability of A given B. You do the probability of A and B again over the probability of B. So this time, this is all in words, and I know how much y'all love word problems, but I need you guys to pay attention here. So in Salem, 82% of the households have cable television and internet access, and 90% of the houses have cable television. What is the probability that a house has internet access given that it has cable television? Okay, so it's asking us. So this is what I want you guys to notice first. We're going to write this out. So we've got the first statement right here. 82% of the households have cable and internet. Okay, y'all see that statement right there? So the probability that someone has cable and internet is 82%. So I'm just going to write that as a decimal, okay? And then it says 90% of the households have cable television, okay? As well. So the probability of just cable is equal to 0.9. So remember, what we're going to do is put the probability of the and. So we're going to do the probability, and we're just going to abbreviate cable and internet over what? The probability of cable, okay? So, and you're going to see how this applies. So then it says, what is the probability that a house has internet access given that it has cable television, okay? So what we're going to do is we're now just going to put these numbers in our formula here, right? So we're going to put our 0.82 on top, and we're going to divide that by our 0.9. So that's all you're doing here, okay? So when you do that, you get 0.91, which is equal to 91%, okay? So we're going to do another one just for practice. It says at Bay High School, 60% of all students have a car and an iPod, okay? So here again, we've got 60%. So we're going to say the probability of a car and iPod, not that anybody has iPods anymore, is equal to 0.6. We'll say iPhone. That would probably been better, right? Okay, and then we've got 70% of all students have a car. It's a large percentage, y'all. So the probability that somebody has a car is equal to 0.7. Okay, so now remember, what are we putting on top? Our and statement, right? So we're going to put our 0.6 on top, and we're going to divide that by our single statement, which is our 0.7. Okay, so we're going to divide 0.6 by 0.7, and when we do that, we get 0.86, which is 86%. Okay, let's see if you guys can do this. You try right here, number 5. And I don't know what happened to you try 6 and 7, 6, but it should have been 6, but that's fine. Do number 5 right now. Come back to me when you're done. So this one says in a neighborhood, 60% of the houses have a garage and a fence. Okay, 60% have garage and fence. Okay, so where do we put the and? You got it on top, right? And then 80% of the houses in the neighborhood have a garage. Okay, so we got the 80% have a single thing, a garage. So that's the 0.8. So what's the probability the house has a fence in the backyard given that it has a garage, okay? So that's going to be 0.6 divided by 0.8. And that's 0.75, which is 75%. So our answer was C. All right. You try, this should have been 6, but it's 7. So let's see if you guys can do this again. Pause the video, come back to me when you're done. Okay, this one's backwards. You all notice that from all the other ones we've done. So 70% of your friends like Coke. So that's going to go where? On the bottom, isn't it? Because it's one thing. And then it says 35% like Coke and Pepsi. So the 0.35 is your and statement. Y'all see that and? It was even in bold. It goes on top. So that's going to be 0.5, which is 50% of people who like Coke also like Pepsi. Notice the wording of this is different, right? So but again, it's asking you what percent of those who like Coke, that's the given part, y'all, is the Coke. Y'all got it? So that's why it's going on the bottom, because that was the given part. Also like Pepsi. And this is the way a lot of questions were worded in the Delta Math. So here's our last one. It says, if A and B are independent events, the probability of A given B is the same as the probability of A. So what does this really mean? So this one means, so we want to see this word independent. Y'all see this independent? So it's saying if A and B are independent, it's the probability of A given B is the same as the probability of A. Why? Because ultimately, if they're going to cancel, if B's already occurred, then A is the probability. Okay, well, let's just talk about this like this. So it says if C and D are independent events, what is the probability of D given C? Okay, so if C's already occurred, which is what it says, we're given C, then we know that it's the probability of D. Okay, so if we know they're independent events, so that's how the answer works here. If they're independent events, it's the probability of the single thing given that C's occurred. Okay, C and D are independent. Where's the probability of D given C? It's just the probability of D. That's it.